Okay. Oh, and can you also give me permission to share on screen? Let's do this one. Now, of course, it starts on the other one. One sec. Okay, we'll do that. I'll just be looking to the right for the whole thing. That's fine. Okay, can everyone see the presentation? Okay, sounds good. Thanks. Oh yeah, I forgot. I tricked you. Don't go off mute. Okay, sorry. Okay, so hi. This is welcome and thank you for coming. This is a presentation I like to call Blueprints for a Serpent. And a working title was also How to Make Snick, and that will come back soon. If you're not familiar with the meme, it's pretty funny. But otherwise, we will keep going. So a few points of order. Introductions. I introduced myself at the beginning of the meeting, but I'm Taylor Bird. I write computer programs for a living. I have been doing it for like going on 13 years now. I don't say that to try to say that that means something skill-wise, but it mostly to say like I've seen some things that work and I've seen some things that don't, and learned a lot more from the ones that didn't.
Hey, Taylor, sorry to jump in, but we're seeing your Zoom tab, not your presentation.
Oh, okay.
Yeah.
Well, that's going to be confusing. Okay, thank you.
Mm-hmm.
How about now? Is this better? Oh wait, no, it's not because I didn't press the share button. How about now? Is this better?
Perfect.
All right, thank you so much, Ira. Sorry. So yeah, so my name's Taylor Bird. I've been coding for a while. I've mostly been doing it in Java and JavaScript, and some more like enterprise applications with a database backend, some middleware, and just learning more and more about the kind of plumbing that glues that all together. I guess DevOps being the term now. But since that gets reinvented every year, it seems it's still fresh and fun and interesting. But lately, I've been getting more into data science and machine learning. And because of that, I've been doing a lot more Python coding. So that kind of leads me to why I'm giving this presentation tonight and why I've gotten more interested in the topic. So I like to stay curious. I like to try to solve new problems and look for solutions and try to understand things at a deeper level. And so I found the company about 7 years ago that has a lot of people at it that share those values as well. Some of them on this call because they're awesome and supportive. And if you come to PyDistrict often and know Vic more than case in point. And I like actually over the past year, just on a side note, because I haven't enough time to talk about it, do also feel like over the past year, other values that caused me to feel like it was a good idea to join Excella are that putting safety and health first, and also kind of liberty and justice for all is not just words that we have kids recite in primary school. So I'm really proud to be at the company. I second Vic's suggestion to look us up. We do solutions with digital services delivery, as well as systems modernization and data and AI projects. And we also help organizations with their agile practices. So now I'll move on to presentation. Clicking. Okay, there it goes. So why talk about different implementations of Python? Why talk about Python specification? Actually, I didn't know this until I got about halfway through preparing for it, but in a lot of ways, it's because of my late professor, Bob Noonan. He was a professor for the comparative programming languages class that I took at William & Mary. He was also the co-founder of the CS department at William & Mary. So in two ways, he sort of directed the path of my life in this direction. I had we weren't super close, but I did learn a lot and kind of got my horizons expanded by his course. We did like a Sudoku solver in Haskell and Perl, when the only languages that I've been working on before that time were pretty much the ones that were in my other CS courses, just like C++ and Java. So it really started an interest in me about other programming paradigms and how programming languages work and how they execute on machines. So this is just a sort of a dedication. All right. So because we're talking about implementing programming languages, this is a broad and deep topic. There's a lot to cover. I ended up finding that there's just too much to do justice to, and more than I could possibly kind of absorb and learn enough about to say intelligent things about that would cover all the topics that are there. But I did take a lot of notes, and not all of them fit into the presentation. So I actually created a companion repository for this presentation off my GitHub. And if you go to that, you will see that there's sort of an organized outline of notes. And I have like a source material, as well as additional references that you can go to if you want to go deeper into the kind of follow my path and then go beyond it. So I invite you to check that out. It also has there's going to be an example at the end of this. I hope to have a demonstration if everything goes well, and it's there too, and you should be able to get it working on your machine as well. All right, so language specifications. Language specifications are a good place to start when we're talking about different implementations of Python, because if we only had one concrete implementation of Python, this would be a very short presentation. A language specification is sort of a consensus for what is the language and what isn't it, right? So it's kind of like, well, asking that question, what is Python really? Or what is Java really? Any language that has a specification or even a standard attached to it. This allows different people to build the language or different versions of the language, and then still have it work pretty much the same way for others who are using it. So things that tend to stay the same across different implementations of a specification are the syntax, the types, and the semantics. So it's sort of like, what are the symbols that you're allowed to use? How does the language treat types? For Python, it's like how do you have lists and dictionaries, and you've got tuples, and you've got all of the basic types as well. And how does that interact, and how does it function? Semantics is more like how does exception handling work in this language? How does it take memory addresses and map them to the instructions and the transformations that take place while the program is running? So it can get detailed, but it doesn't have to be so prescriptive that you can only do it one way. And that's sort of what this presentation is about. Things that tend to change across implementations are the way that the language is either interpreted or compiled, how the language runs, so the runtime execution, runtime environment, as well as sometimes changes in those features or aspects of the language can result in new language features that you don't get with your basic reference implementation. So I have a little asterisk because in some cases you can have a language where you don't drift too much with syntax, types, and semantics, but it's still pretty much the same language. It's close enough to be right. And there's varying degrees of strictness to which you can do a specification. I think specifications and standards are almost synonymous terms, but we have groups like ISO and IEEE and ECMA and ANSI, which actually standardize languages very formally. They say, almost to like a mathematical standard, this is how the language needs to be able to run so that it will be exactly the same. If we have a decimal here, it's going to work exactly the same way if you implement it according to the standards. And they even call out when you're not on standard and not compliant. But Python's a little bit looser than that. We'll talk about that soon. So the reference implementation is sort of the core implementation of the specification. It actually usually comes first. It precedes the standard, and it is, in most cases, I guess you could come up with a specification for a language and then write a language to that spec but that's usually not how it works. I think Perl famously had like 6 years before it had a specification written for it, but it was a language that you could use. So people tend to come to think of the reference implementation sort of the concrete companion to the specification. So for example, in the language reference for Python, if you go to their language reference page, you'll see that they have a lot of annotations just about the fact that, this is how cPython does it. The semantics for Python are actually natural language. They just describe how the language is supposed to function. But they also have test suites to make sure that for a specific version of the reference implementation, which is cPython, you can run those tests on your implementation and they'll pass or fail. And that gives you a sense of whether or not you're at least mostly meeting the feature set that you've set out to duplicate. So the reference implementation is usually the one that is used by the most people. It's usually the one that is the most up to date. In Python, this is definitely true. So if you're using something like cPython and you want to make sure the new people on your team are able to get up to speed quickly, don't necessarily change languages, and or don't change implementations of Python, and we'll talk about that again a little bit later on. But generally speaking, this is the target, and so it's the one that is the safest to use, the most general purpose, and the one receiving the most maintenance and the most updates. So how come we even talk about having more than one implementation of Python? We have cPython. It's great. Everybody loves it. I love coding in cPython. Whoa, I really had to say that second part to make that honest. No, but and so why even bother opening up a language to be implemented in different ways according to a spec? Well, it's actually really handy to be able to do this. cPython isn't designed to do everything for everyone. It's designed to do most things for most people. And Guido van Rossum who is the original author of Python. In case you weren't familiar, he's also the benevolent dictator for life. He was up until a couple years ago, I believe. And he has been working on cPython for a lot of his life, and yet he's someone who might be the first to call out that PyPy is a good choice for certain scenarios, or you could consider using Python for that. So that's just to go to show that Python actually has a history and a creator who is more interested in the possibility for extensibility. It kind of goes back to the creation of the language. Python has been, so when Guido van Rossum was working on a language called ABC in a group, I believe it was like CWI was the company he was working for. They had this language ABC and he really liked it, but it wasn't extensible. So there were some things about Modula 2 and Modula 3 that he really liked, but couldn't add to ABC because it just wasn't possible. And then they were working on another project as a distributed operating system called Amoeba, and Amoeba system calls were difficult to reach through bash scripts. And so he had this issue where he's like, well, I can't use any of these three the way that I want to, and I could write a bunch of glue code to make it possible, but that would probably be very error prone and break often. So he opted to just write a new language with the syntax of ABC and some of the features of Modula, and then Python was kind of created out of that. So you can see like the history of Python is sort of one that invites experimentation and extension of itself. So no, but really though, what practically why isn't it enough to have one implementation of Python? Well, there's a lot of reasons you might, but we're only going to cover a couple of them. There's about 4 recognized variants. Like if you go to the python.org site and say, what implementations are meeting the spec for Python, but they are different. You'll see PyPy there. You will also see Stackless Python and Jython and IronPython. And I think Python.net, could be wrong about that. But those are the ones that are sort of recognized, and we'll cover those, and we'll also cover a couple more. But there are different reasons why you might want to implement one. So cPython might not meet performance needs. PyPy has a solution for that, and we'll talk about it. Cython as well. There's one called Numba, which used to not be as popular as Cython, but now I think may have surpassed it based on LLVM. And if you want to have Python communicate with other languages such as Java or C# or ASP.NET, then you can also you can use Jython or IronPython as well. If you want, what about if you just want cPython to be a little bit, you just disagree with something about the implementation of cPython and you think that you could make it better. So you're free to implement something. It may not be something that cPython thinks is part of the standard or something that would be good for the most people, but it might be really good for the use cases that you're considering. So stackless Python I think would be the best example of that. PyPy is kind of an example of that as well. And then I put in one that is just sort of a thought experiment of what if you just wanted to make Python more functional? You want to make Python more logical. You could do that. You could implement a language that meets the spec mostly. There are some things at the level that might just turn it into a new language, and then so you'll get something like Elixir or Scala, but for Python. But it's out there. There are possibilities. They haven't all been exhausted, and that's exciting. So, what is typically what do programmers care about? What do I care about when I'm running programs? It's mostly I just want to write source code, and then I want to test it as fast as possible, and that's one of the reasons I'm using Python. And then I want that program to run and have the functionality that I asked for. So that's all well and good, and you can get by with just that. But in order to talk about this topic, we do have to get a little bit deeper. So I will be going into a little bit more about how things work under the hood in the middle of this diagram, I guess you could say. Okay, yes, we do. All right. So this slide might be the most important foundational slide for the rest of the presentation, and possibly just the rest of it sort of derives from this. So this is something that it's kind of a mind bender if you're just thinking about it for the first time, and then it gets more and more comfortable. It was confusing to me actually as well, because when I think of virtual machines, I've always thought of emulating the entire hardware or the entire operating system or having a kernel. And that's not exactly the way that a virtual machine for a language interpreter works. So I'm just going to go from the beginning. What a very important first step is you have to go back in time. Most of us think about the center panel in this slide, which is that the programmer is writing a program with something in mind, hoping that they'll execute it and it will work. But there are two steps that happen before that that make Python a little bit special. I'm going to talk a little bit at a high level about some definitions. There's, languages could be compiled, languages can be interpreted, and then languages can also be interpreted but compiled while they're being interpreted, and they can be compiled and then interpreted. So there's a lot to unpack there, and sometimes I think it gets really confusing because you'll just talk about an interpreted language without the fact that compilation is taking place, and it gets a little bit hazy to think about it. So first, we'll talk about the fact that it could be compiled. So languages like C and C++, strictly compiled, right? They're compiled down to machine code, and then you run the code separately in a runtime environment. So there's a build time environment and a runtime environment. Languages like Bash for shell scripting, they're purely interpreted. You write it's a program that can run your commands directly. Every time you write a statement, it's immediately all of the steps that we're going to go over in the 1, 2, 3, 4th panel on this slide take place immediately, and then it runs in your shell. And then there's a middle ground, which is where Python, Java, Ruby, and other languages live, where you have a compilation step down to an intermediate language, like often called bytecode. And then you have the interpretation of that bytecode done by another program, which is usually strictly compiled, but doesn't have to be, I suppose. So in Python's case, it is interpreted, but it is compiled as well. And let's talk about what that means. So the interpreter author will write an interpreter, which is actually, in the case of cPython, it is a C program. So it's a compiled program that compiles all the way down to machine code, and it's compiled to a specific target architecture in a specific platform. So if you have interpreters, you need to have an interpreter that will work for the platform that you're running on. So that's an important step. So this, just remember that you're writing the C program first. The C program knows how to run on the target hardware. Then a programmer will install the version of the interpreter that matches the platform that they're on. If they're on Mac, if they're doing a Unix operating system, a Linux operating system, a Windows operating system, x86, x64, they are going to download the version that corresponds to what they're using. So now you already have the C program downloaded and installed on your machine that knows how to read a language, which is bytecode, and then translate those instructions down to the target architecture. Then you write the program we talked about, and this is where you can be a lot more ambiguous, and you don't have to, it's a lot, you're trying to get as close to natural language as possible, really. If we could just talk to computers and have them do what we say, that's probably the best case scenario. And then the interpreter will first go through some steps to compile the language down to bytecode at runtime in Python's case. So when you run the Python program, I don't know if you guys can see my pointer or not, but say you have run a Python program, it's going to first tokenize your program into several different tokens. It's then going to determine which tokens actually matter and which don't to the computation you're trying to do. Then it's going to create a sequence of the tokens that do matter. And it's going to lex them, so it's going to make sure that they all fit into the grammar, throw some errors if it doesn't. And language grammar is another thing that you can check out the repo if you want to learn more about. And then there's a step which is syntactic analysis. So that was lexical analysis, it just happened there. Then there's syntactical analysis, which is taking that sequence of instructions, or symbols rather, and converting it into either a parse tree or an abstract syntax tree. Python creates an abstract syntax tree. A parse tree is a lot closer to the grammar, and it supports different ways of saying the same thing. So it's a little bit more redundant and can be ambiguous. But an abstract syntax tree can in some cases almost be language independent, because it's really just it's what the underlying program needs to know to be able to run things. So it's strict computations, unambiguous. And then that step, the semantic analysis, is followed by breaking down the abstract syntax tree into the bytecode instructions that will ultimately run. And so like these instructions are more instructions saying, load. And these would be like memory locations. This would be instructions for what to do with the runtime stack. And then after that whole step's been completed, you have the compile step done. So then you move on to interpreter, and the interpreter is going to take in these instructions in just a while loop that runs continuously, and it is going to it's going to then execute them with the same interpreter code that was written way back in step 1. So you can see that while these instructions are actually machine independent, this interpreter program knows how to execute them and then produce the desired result. So sorry we spent a long time on this slide, but I do think it's important to go over because all we're going to talk about for the rest of this are ways that you can mess around with this process and all the benefits and issues you might have. So what can you change about this, and what are the outcomes of those changes? Well, let's go over some known ones, some major known ones. So the first thing you can do is you can get rid of the stack. So I'd mentioned briefly in that prior slide that there's a runtime stack in cPython, which kind of emulates the fact that the C program that the interpreter is running on is using a stack. And so the interpreter, the bytecode instructions and the like breaking up the transformations that need to take place of the state of the program, that's all being done on the same stack as the C program. But if you have a small insight, you can see that there's actually no need for the bytecode instructions to be on a runtime stack in the first place, because the C program needs a stack. It's a low-level programming language. It's using that to organize its memory. It's using that to organize what local variables are, how to execute, what order to execute things in. So it needs that data structure to run properly. But this bytecode, I mean, we're pretending it's a machine. This interpreter program, we're pretending it's a machine. So it's actually running this bytecode, but it doesn't have to run it with a stack. You can do things to kind of extend it and run different data structures, such as you can put little pointers into the runtime stack to say, okay, well, maybe start running it here, but then actually store and allocate dynamic heap space for the execution context of functions, so that they're not actually on the stack. There's just kind of the stack just becomes a place to refer back to, so you don't accidentally step on yourself. So why do that? Why make that change? So, well, a stack is first in, first out, and everything that's executed. A stack is optimal for running something called a subroutine, where the inputs to a function are processed, and then the outputs happen, and then the next thing happens, right? Because you push things onto the stack, you pop a couple of things off, you execute them, you push them back on, and you pop them off again, maybe with something else, you execute and push back on. So they're optimal for functions that have a defined start and end point. That there's only one way to enter them and one way to exit them, depending on how the program was written. So the only way to get around that in a lot of other programming languages you may know is with threads, right? So if you're on a main thread when you start your program, and it has its own stack, and if you want to pause execution in the middle of a function and do something else, then you can start another thread that has its own copy of the stack. You can suspend the state of the function that you were executing before and hold on to it, let the other thread execute, and then, or have the operating system more likely preemptively take control and give it to another thread, let that thread execute a different thing, and then give it back. And this is another way to achieve a similar purpose of what you would get with removing the stack from the Python program, where it's in stackless, you have something called continuations, where you're kind of doing what I just talked about with threads, but you're doing it at the level of the stack frame. So you don't have this overhead of creating a whole nother stack and then a whole nother thread and having them talk to each other and having them pause its execution. You probably have fewer issues with threads, grabbing the same data. There's a lot more, and you can do cooperative as well as preemptive multitasking, which means that sometimes you can have the operating system decide for you without you doing anything that you need to go to a different coroutine or different continuation rather. And sometimes you want to have functions defer to other functions and cooperatively share execution paths. And this is actually really powerful. It's hard to describe how powerful it is. So I have some examples of what you can do with this. So EVE Online is an example of a game that's been around for a long time. And it's kind of made stackless Python famous by being able to run a single server, a single game world. And like, it is a very large supercomputer that's doing this, but it is running a single thread, and it is able to support thousands, 10,000, I think 40,000 might be the record of concurrent users in this giant, massively multiplayer role-playing game. So you can imagine lots of people on this site all at the same time performing actions, and this is allowing them to do it in a way that doesn't slow down enough to crash the system. Another example that sounds really interesting, but I probably want to learn more about, actually two of them. These two I didn't get as much into, but I do think they're very interesting. One is the idea of you can pickle the state of one of these tasklets, which is a way to refer to like these parts of the stack that you were running and then deferring execution on, you can pickle the state of them, and pickling, if you're not a Python developer, I guess would be more like serialization, if I can think about it that way. And then you could actually send it across to a remote machine and execute the rest of the function on that, as long as the interpreter version is the same. They could finish executing that function on a thread on their machine. So you can have programs, you can have clustering, you can have programs sharing function execution and control flow. And then Nagare sounds amazing, and I want to do some more with it. It does it sounds like it inverts the paradigm of working with web applications. We're used to web frameworks that were MVC for a long time. Now I feel like React and Angular are making that a little bit less the case, but even so, even as though they're component based, there's some ways in which they're still doing a lot of the classic things that web frameworks do that kind of get in the way and doesn't really feel the same as doing a desktop application. Nagare promises to kind of move some of that away from you and turn it back into an imperative desktop application style program by treating the browser as something where you would pause execution on it, and like you think about, like, you render your page and then you wait for user input, and so that's pausing a continuation. And then once they provide the input, then all of a sudden you have all these different components that are rendering views, and then those views are getting sent back to the browser, and you're able to write the program a lot more imperatively, and not without all of the request handling that happens and all the different controllers that are spread out, and the control flow is fragmented and spread across several different files. So that's pretty cool. And yeah, I want to learn more about that as well. So another thing you can do, let's talk about PyPy and RPython. This is, there's a different set of insights for this. One is, what if you, instead of writing your interpreter in C, you restrict Python to a subset of Python called RPython, and that allows you to do static analysis of types. If you were to do that, it's actually, well, it's been proven now. It's possible that you can write an interpreter in Python that will interpret Python programs. So the interpreter is written in RPython, and the program, and we talked about how a C program is compiled. Well, the RPython interpreter is compiled by a toolchain that's written in Python. So once you have compiled the RPython code into an interpreter, it's actually optimized so that it can basically be reduced down to a lower level language like C. And if you provide some interpreter hints in your code, it's the PyPy.
Join the meeting.
Oh, sorry. If you provide some hints into the interpreter code that you write in RPython, then PyPy project has also created a way that they can use sort of the flow-based annotations that they do when they're compiling the RPython down into an interpreter, to, at the same time that they're doing that, create a just-in-time compiler that can handle new Python bytecode coming in and directly detect hot code paths and convert it to machine language, so binary code on the fly. So you can get a lot of speed up that way. And the third part, which is really interesting as well, is that if you you can write other languages in RPython. You can write an interpreter for a new language you come up with. So maybe you have this idea of this language called Crisp that's like C and Ruby and Lisp all mixed together, right? So, but you want it to be dynamic and you want it to be interpreted. So maybe you can write it in RPython, and you can use this tool chain, and you can add some annotations, and for free you get a just-in-time compiler that's generated for your new language. So it's a language-independent framework for kind of generating just-in-time compilers. It's very kind of very different from what a lot of others are doing in the space. What do you get for that? Well, PyPy is very fast. It's got an average 4.4 speed up across the different benchmarks. That actually, cPython tests itself against benchmarks for libraries that use it frequently, and PyPy is able to outperform on a lot of the benchmarks. They're slower on some of them, so it's kind of, it can be a trap. It's not always the right solution. Another point is that PyPy is actively maintained, and they maintain a test suite that keeps compatibility with cPython up to version as of when I read about it, it was 2.7.18 and 3.7.9, which is pretty good. We'll talk a little bit later about how a lot of these implementations are really lagging behind. A lot of them are still doing 2.7, and Python's trying to deprecate 2.7. So, but that's you're not dealing with something that's going to go away tomorrow, most likely, and it's going to have a lot of the features that you're used to if you're working in cPython. One downside is C extensions need to be recompiled. So if you have, and I think that PyPy generally is really trying to catch up and not doing as great of a job with working with C extensions. I think we might talk later about how they prefer CFFI, which is slower than what you might get if you used Python or something else to create your C extensions. So that's one other thing to be mindful of. Oh, and it can also do stackless Python. So all the things we talked about with stackless Python, they have an implementation as well. It's a little different. It's called stacklets, but it does a lot of the same things that stackless Python can do. Okay, and this may be the last one that's major. We'll talk about IronPython and Jython and the general concept behind them. So first insight to have here is that once you get down to bytecode, then the virtual machine executes the bytecode, right? So Python syntax and Python semantics could be compiled down into a different bytecode than Python bytecode. So it could be compiled down into Java bytecode. It could be compiled down into the intermediate language that .NET languages like ASP.NET and C# use. So what does that give you? Well, actually, we'll talk about what it gives you in a second. But so you can just use the virtual machine that's been set up and the runtime environment that's been set up for that language to execute this code. And you can think about how that might immediately be interesting. One of the cool side effects of doing this is that if you're using the Java virtual machine, or if you're using the common language runtime from .NET Core, you're going to have no global interpreter lock. I've learned a lot more since starting to, when I was outside of the Python community, I thought that was a big deal. I've been learning that it's not as big of a deal, maybe, and that it's becoming less of a big deal as Python updates itself. But it's kind of interesting that it just goes away, which has been difficult to remove. PyPy is trying to remove it and can't. So if you want to learn more about the global interpreter lock repository. So IronPython Java, what does it give you? Well, this is really interesting and fun, and I wish I'd known about it years ago. You could start up a Python interactive shell. You could do a REPL with Python, where you have access to C# assemblies or Java libraries. You can write nice, easy Python code that tests out these libraries. So you want to experiment. Now there's REPLs for, I mean, Java has a REPL now since 9, but it's still Java code, which can be a little bit more verbose, right? And it doesn't have quite the syntax that Python has for productive coding. So this is really cool sounding to me, and I've never experimented with it, but I think it's really neat. So that's one thing, sort of like productive prototyping and interactive testing early with things you might want to try just in a shell. Then also you can embed Python interpreter code, and you can basically have a Java or .NET application that runs Python-like scripts and exposes Python-like scripts. So your backend might be Java, maybe you're more comfortable with Java, but then you have the ability to write modules and have clients write scripts and modules that will run with your code. And so embedded scripting languages are useful for a variety of applications, and this is one of the ways you can achieve that. Faster, it's faster, makes people more productive, and sorry, I just want to check to see what my last note was about here. Yeah, oh, there was a really interesting example of of someone who was using Jython, and they were setting up a test bed where they were essentially running their Java program, and at runtime they were doing things with Python and in Jython that were causing changes to the program at runtime, so they could observe those changes and perform assertions on it. So that's, we all know that like when you're running automated tests, a lot of the times one of the most annoying things is faking, stubbing, mocking, and you can get yourself into traps where you're not really testing anything. So Python, what if you could do it in Python? You could probably write a lot better fakes a lot faster, and you could also run your program and make changes to it. So that was a very neat idea. Okay, and then Python I want to touch on because coming from the data science community, I thought this was also really it's something that's being used a lot, and Numba as well. So C extensions and C++ extensions have been around in cPython for a long time, and allows you to essentially, and cPython uses them for like its built-in types, some of the built-in functions that it has, because then you can run the highly optimized version of the code. So once it's stable, you can just move it down into C and it runs a lot faster. So Python gives you a way to, it's a superset of Python, and it allows you to write Python with declarations embedded inside that show you ways you can optimize the Python code, and the Python compiler will compile that code down to a lower level language, C, and then make it so that it can be dynamically linked back to the interpreter when you're running your code. And that's part of the example, so I won't talk too much about it. All right, so these sound really cool. Why even use cPython anymore? We're getting close to the end. Bear with me. I'm sorry. So cPython is going to be around, and it's going to have the latest features, and it's going to probably be trying to target things that are going to make your life easiest as a Python developer. So jumping onto a different implementation because it's got one cool feature, instead of checking your use case and doing your homework to make sure that it will actually work and actually improve things, may not be the best thing. If you're working in a team environment, it's much better to start with cPython, see if it's good for your use case, and then think about whether or not you want to try PyPy, because it could really benefit you. There was a great talk, I have it saved in the repository, which is a group that does flight recorders. They parse flight recorders, and so they've basically written something that is doing this thousands of times a day on really, really long programs that have very confusing parsing steps and involve various amount of data analysis in them. And that, because of PyPy's gains in speed, they were able to get orders of magnitude improvements in their productivity. So of course they went with PyPy. But that's not everyone. I think developing web applications, PyPy doesn't actually work as well for some of that because it's heavily about network traffic in the database. So those things are not optimized by PyPy. It's more about your procedural code that you're running in between. So yeah, don't become that teammate who gets blamed when you shift it over to the new technology. All right. So there's a lot of variants we didn't cover. In fact, thank you at the beginning of the conversation talking about Rust Python. I didn't even know about it actually. And here are some other ones that are out there. So Numba is like Python, but it's based on the LLVM. It doesn't compile. So Python, you compile something into an extension and then you attach it. You have to have a compile step first, which is kind of not very Pythonic. Numba, you annotate, say, I want to just-in-time compile these sections of my code, and it will do that for you at runtime. The Python.net is kind of like the other side of Iron Python. Iron Python is more like backed by Microsoft. Python.net, while Iron Python is more about the getting Python to work in a .NET environment. The other Python.net is the other way around. I hope I said that right. Shedskin is if you're interested in gaming and you want to write Python code instead of C++, maybe check this out. It is similar to what we talked about with Python, where you have these annotations and there's a superset of the language, and it allows you to provide type information to Python code, so it'll run a lot faster. And it's actually winning in terms of speed. It's just that it's behind on Python versions, and I guess not a lot of people need it for its specific use case, and the scientific community is going all over the place coming up with optimizations, so they don't really need it either. Scientific being like data science, machine learning. Starkiller was an MIT thesis that actually got an implementation, but it was all the way back in 2004 before a lot of these other ideas surfaced. And it is not, no one ever picked it up and turned it into something. It kind of is a short way of saying that. And then RubyPython is an interesting one to call out just because that is, you have a Ruby interpreter and a Python interpreter running simultaneously, and there's a bridge between them that allows, it's kind of, you embed the Python interpreter into the Ruby one, and you use FFA, I forget that foreign function, FFI, foreign function interface to send the bytecode back and forth, and so that the bytecode is interpreted by the interpreter that knows how to interpret it, and then you're able to sort of have communication across those two languages, so you can write the code together and run it all at once. Okay, this is attributions page. I just wanted to mention most of these things were already kind of fair use, but there was I used a lot of stuff in the presentation, and if you're interested in checking out the sources, it's all there. All right, I probably went over time. I'm guessing I did. Oh, I have 3 minutes left. Okay, so I know that I was probably a whirlwind, and I probably didn't describe some things in the most clear way. I could go to questions now, or we could go over the exercise.
We have this space for, I think, at least 2 hours, so you can go for as long as you want, Taylor.
Great.
That's correct.
Thanks. That's fantastic. So I think I'll start with the exercise. Yeah, that's what I heard. So we'll do it. All right, I'm going to move over to this screen. That looks right. Okay. Sorry, people are getting picture in picture in picture in picture.
Right now, we're only seeing your PowerPoint window.
Yeah, because all right, I'm going to move this stuff over here. Okay. All right. So, one thing I wanted to show before this is, so if you're interested in benchmarks, because I actually did this presentation once before and got some questions about what are the actual performance benchmarks and how do I figure that out? And I think that's a great question. So I just wanted to touch on that. So there's a Python Speed Center, which allows you to compare versions of Python. So Python, this is more about just cPython. And then PyPy, which is the only benchmarking thing that I was going to refer to, is maintains a very similar site. You look at them; they have the same domain. They have very similar interfaces. And then the comparison tab allows you to compare PyPy to the latest version that it's compatible with from cPython. So let's give that a shot. I'm going to first normalize everything against cPython 3.7.6. That's the one I'm interested in knowing about. And then I'm going to turn everything off because there's way too much information here. And then we'll activate cPython 3.7.6 and see all their benchmarks across. This is across all the ones that PyPy did. And then we will pick PyPy 3.7 with just-in-time compilation. And then it's still kind of hard to see, so let's do horizontal view. And now we're getting somewhere. So let's see. So if the colors are hard to distinguish, I'm not. The bars are very thin. Sorry about that. But the top bars are all PyPy, and the bottom bars are all cPython. So you can see that on a number of benchmarks. Well, why is cPython exactly the same on every single one? That doesn't sound right. Oh, because it's normalized to it. There we go. So we're seeing PyPy compared to cPython. This is good because sometimes PyPy is so fast that it's only like a millisecond, and then cPython is so long that it would be too difficult to visualize. So as you can see, like PyPy is winning in almost every category until you get down to the bottom. And some of these down here are like SymPy, which is about using, it's actually really interesting. I guess it's for people who do a lot of things with actual mathematical notation. So it allows you a way to run things that are kind of like LaTeX, but then like a LaTeX notebook, if you can think of it that way, where you can use math expressions and then evaluate them. So for some reason, PyPy is way worse at that. Also Sphinx, so that's document generation. It's kind of like the read the docs pages that you'll see. Python has a lot of those in that. Sphinx is a lot slower in PyPy as well. I could venture some guesses, but I probably wouldn't know the real reason. And then it's much faster across a lot of other things. So your bet is kind of good that you're going to get a performance improvement with Python, is the big takeaway for that. Okay, and I'd like to go to, well, this is the repo if you want to go and check it out. And now we'll talk about the exercise. So I tried to create a hypothetical example for this because I like it when something seems like it could really happen. So, but this is kind of far-fetched. So, and credit to Ben, who's on this call, for the name of the band used. So if say you have a favorite band and the band is strange, they're kind of like Willy Wonka, maybe maybe Ready Player One would be a better analogy for nowadays. But they've decided that instead of releasing their new single on Spotify or one of the other platforms like Apple Music, they're going to go ahead and create. They're going to take the binary of their audio file. I don't know, maybe it's encoded. I'm not good at that stuff, so I don't know. And they're going to slice it up, and they're going to distribute the ones and zeros across a bunch of other long strings of ones and zeros in a seemingly random distribution. But there's going to be a pattern such that if you know how, you can find out which of these strings contain actual parts of the song and which ones are just noise. So this is a difficult challenge. They've said, you know, we'll give you a cash prize if you're able to figure out which one, if you're able to repiece the song together. Don't ask me about how you would do it in order, but just bear with me. And then they've provided you with a list of 300 strings of ones and zeros, 100 of which do contain a piece of the song and 200 that don't. So now you have a labeled data set. So you're thinking, okay, maybe we could apply some machine learning here, right? So what's a good machine learning for long sequences of data? Well, reading about it a little bit more, you see that in, I guess, bioinformatics and other fields dealing with gene sequences, and there's a string kernel that still has popular and widely used, and it's kind of not going all the way to using a neural net, which you won't understand if you need to figure out why something worked. So you say, okay, let's use string kernels.
Taylor,
okay.
Can I jump in? There was a request for increasing your font size a little, so.
Sure. Thank you. Can anyone tell me to do that in Chrome? Control plus. Okay. Thanks. Is that better?
I believe so. Yeah.
Great. Thank you. So now you've decided to use this string kernel idea and apply that with a support vector machine. And there's actually, if you want to learn more about what that, I'm not going to talk about really how that works. For this, it would take a long time. But if you're interested in how it works, there's a really cool YouTube tutorial on it that I have linked in the exercise if you go to the repo. So the problem is you start like a good programmer, you don't just start to write it from scratch. You go looking for existing implementations, right? So you start with scikit-learn and natural language toolkit and look for all of these other Python-based machine learning and string comparison libraries. Maybe you find VIX and for string distance and string similarity. But so far you don't see anything in this example. Like maybe this exists, but let's just say you can't find a good implementation of string kernels. So you decide to take the white paper that this was based off of and implement it yourself. And someone did this, so that, and I am taking their code, but they shared it under a completely open license. So, but I do have attribution here. So anyway. So this is the paper, Lodi et al. 2002 for string kernel, and it defines a string kernel with some pseudocode and formal kind of mathematical notation, and you implement that in just straight up Python. As you can see, you're using NumPy though, so you have a library. I didn't get into the fact that like OpenBLAS and a lot of other optimizations are applied to a lot of these libraries. Use C extensions, they run fast, they turn off the GIL for certain operations and parallelize. Like, so the scientific Python has a whole slew of like performance benefits that isn't implementing a separate language of Python. And you're going to use some of them here. So, but even though you're using NumPy, you still have a lot of this procedural code to do. Here we go, like for loops, one of which is nested, you know, and it's all dependent on the length of the strings that are coming in. So as the strings of binaries get longer, you're going to have slower and slower implementation. So I've gone ahead and generated some example strings that you might be real examples in this hypothetical, or might be something that you're just using the prototype. And I'm going to go ahead and run that. And then I'm going to put in some profiling code to see exactly how long it takes for cPython. But it's not going to be difficult to see that it takes a while. Oh, and I do need to import libraries first. I separated that out, and we'll see. Okay. So now we can all go get some water. Wow, that was embarrassingly slow. 20 seconds. 20 seconds is, I don't know about everyone here, but like when you're working on projects where you're communicating over the internet, you know, or trying to load a web page, what isn't it like less than 2 seconds for someone to be like, I'm not going to go here, right? So that's pretty slow for code running for this scenario. I mean, if you think about the way that this is going to be used, is it's going to be pairwise comparing all of the strings that you have over thousands of strings, and then applying this like dot product to them, and raising them to an exponent and doing that over and over again. This is going to take a really long time to run when you run it in the support vector machine. So this is just not acceptable. So what are we going to do about it? Well, PyPy. We talked about PyPy. It's fast. Maybe it will help us. I have some instructions how you can set this up, and there's also a README if you want to do this yourself. I've already taken the steps to save time. I'm going to change my kernel to PyPy 3, and then Vic, I think at some point we can get this into go-to code. And now we have PyPy instead of cPython. Let's see how that goes. We'll run the same thing. Maybe I have to run both. And it's still taking a long time. I don't know. This is probably not acceptable either. Probably have to do something different. Wow, it took even longer with PyPy. That is surprising. I mean, these aren't benchmarks, of course. It's just me running something on my machine one time, but that's still too slow. So what about if I go back to using cPython because it was faster? And then rerun the cell because I've learned it. I need to. And let's try Python instead. And there's a little disclaimer here. In addition to just switching to Python, the author of this code found some other optimizations in Shogun, which is another C++ based library for the same purpose, and applied them. So some of the optimization and some of the speed benefit might be coming from that, but I think Python is the clear winner, and a lot of the benefits come from using Python instead. So all you need to do for this we're going to we're going to do this magic string in Jupyter, which is telling us to load the extension cPython that I've already installed on my environment for Python. And then there's another magic string now that we've loaded the extension that says compile this with Python. It's a lot faster to get started with this. If you're writing a C extension outside of Jupyter directly in Python, you need to use a setup.py, and there's additional steps to be followed to compile it, to set up like how will it be compiled down to C, how will that then be compiled to .so, how will that be used. But the good thing about Jupyter is it's snappy and fast. So let's go ahead and run it. Well, not run it, compile it. And now we have a function to run the same, pretty much the same thing we were running the first time. And I'll just show you really quick some of the important things to note here. So see these annotations, they're showing you that you're turning off bounds checking, you're using native index wrapping, I'm saying words. you're also using these CDEF type declarations that are helping Python figure out how to compile this down into C. It's kind of like closing the gap between Python type system and C type system for strict typing. So, all right. Then let's run this one. How far did I go? There we go. Run that. Wow, that was fast. 0.014 seconds. So that's orders of magnitude faster than 20 seconds, right? So there's a benefit to doing this and to using these alternatives at times. You can also, as long as you recompile the Python code, you could use Python with PyPy. Just wanted to mention that as well. So yeah, and feel free to try this on your own. It should work. I used Conda, and I created a README that sets up how to do this if you use Conda. If you use pip or something else or in virtual environment, your steps may be different. I didn't write out the different ways to do it, but that's pretty much all I had for the demo.
Taylor, would you like to take Q&A?
I can try. You will be able to stump me, I promise. So, but yeah, let's go.
All right, guys, we're open for questions for Taylor. Feel free to play. Also, yeah, great presentation. I really enjoyed it.
Thanks. It was fun to make. Learned a lot. This is not something that I was like familiar with before.
How do you want to take questions? You want people to just post in the chat and you just like call on them?
Yeah. Sorry, I've never. Yes, it sounds good. Chat.
Okay, so if you have questions for Taylor, just post in the chat and he'll call on you.
If I can figure out how to make that work. If I'm sharing, oh, there we go. Oh, there's already some. Oh, font size, cool. Yes, Vic. It is. And there are more things I researched and didn't have time. There are a couple of topics that I think are kind of related to this one, which is like how to do concurrency in Python touches some of these implementations and the things that are good about it and the things that are hard about it. And that's like it was just too much to learn about with regards to that for me. So, but I did put a lot of notes into the positive.
I had a question, Taylor. So when we looked at like the PyPy implementation versus the reference cPython implementation, the PyPy, and the PyPy wasn't actually faster. Is that because they both depend on NumPy, and NumPy is one of those like C extension things that PyPy doesn't optimize for?
Yeah, you're hitting me with some softballs. Thanks, Vic. That is one of the reasons I would say like is a strong guess as to why this is not happening that much faster. And I'm also like, I don't know as much about what happens where like you're using normal kind of iterative for loops with NumPy arrays if it is still kind of optimizing that. But I would have thought that like you'd have to call a function off of NumPy in order to like get a range or something where you're taking advantage of its indexing and the fact that it's written in C to speed things up. But I think that is a really good theory as to why this is about the same in both.
DG had a question in the room, Taylor.
Oh, nice, good question. Yeah, so my take on it is that PyPy does use the just-in-time compiler. I think you can turn it off, but it is. I think its use of the just-in-time compiler probably counts for most of its speed. So if you think about you're running something with a PyPy interpreter, it's already like it's taking the bytecode that it's receiving, and if it sees code paths, it kind of builds like a flow graph based off of the bytecode instructions and detects when it sees something happening frequently, and it says, okay, this might be a loop, or because looping is something that causes a lot of slowdowns in programming in general, right? So a lot of what optimizations that just-in-time compilers are giving you is that they're detecting those hot code paths where it's going through a loop and executing the same instruction over and over again, and it's able to say, okay, well, if this is happening, let's just make it machine code now, and that bypasses the whole process of, remember, you're running a program that's acting like a machine to execute instructions that are coming in. It's kind of, if you've heard of like metadata, this is like a metadata programming where it's taking in a language as its data, and it's saying, I'm going to execute the code from this language, and that's going to be slower every time than if you cut that out and you just go straight down to the binary that the machine understands already and can execute on the hardware. So PyPy is doing that more often than not. You can turn off their just-in-time compiler. I haven't seen benchmarks for what happens when you do that. Actually, there are benchmarks on that page that I showed for it. So if it's still faster with that, I think I'd be curious as to why.
Well, let me ask you, Taylor, why could cPython do the same thing? I mean, why don't they do that? Why don't they try to make it faster?
So that's a great question. I think that there are a lot of people who are wondering the same thing, and I think that if I was speaking from the perspective of a Python core developer, I would say PyPy has now diverged so much from the core cPython language. So if I'm developing for cPython and I'm actually adding features to it, there's sprints and you can go and join. And if I am doing that, I want something familiar. And the way that I think a just-in-time compiler could be in cPython's future, but they probably won't do it the same way that PyPy did it. As I described how you have this RPython and a Python toolchain that uses RPython to create a just-in-time compiler for any language that you might want to write with it. That's not something that's really a goal for cPython. cPython just wants to, make really good cPython, and they're familiar with writing something that has a stack, and they're familiar with, so stackless is kind of dead on arrival because I didn't talk about this, but it's kind of a related topic. They took when they were developing stackless, the core developers of that actually discovered that there's another way to do what they were doing called greenlets that is sort of separate from the language and the way that it runs. And then that got infused into cPython. So now cPython has greenlets, which do a lot of the things that stackless did, not all of them. And so now, like, stackless Python is kind of a branch that's being maintained because a lot of people are using it, but it's this sort of alternate distribution of the language that probably, isn't going to, in the long term, I guess, stick around.
Okay, thanks.
Sorry, did that answer your question?
Well, a lot of it, yeah. I mean, it's obviously really complicated. Now, one question I had was, so PyPy won't run regular Python. Let's say you said they're up to 3.6 or 3.7 now. It has to be RPython. It won't run standard Python.
So RPython, you don't have to write in. That was something that tripped me up for a long time when I was studying this as well. So the interpreter is written in our Python, and they use that to be able to make the interpreter code actually compile down to C by that tool chain. But then you write Python code, and they actually, what they do is they use the cPython test suite to verify that they're compatible with cPython up to certain.
Turn a little webinar in the background. Why?
And so it's they won't get up to 394, for probably a while. They have to get grants the way that PyPy does their sprints. I think they get grants to do specific things, and they fund themselves that way. So they've gotten a lot of grants to do things like be more compatible with NumPy, be more compatible with pandas, these things that are getting used a lot nowadays.
I see.
But they haven't, they haven't gotten all the way up to the latest. They'll always be lagging probably behind cPython a few versions.
And I think that touches on one of the reasons why like cPython can't move over to like PyPy, if that was kind of a proposition, was because like PyPy breaks compatibility with some C extensions, and a lot of like some of the core Python internals are written in C, and that's how like Python's like dictionaries are so performant.
Sure.
And if you drop that API, you break a lot of extensions that people have gotten used to. So there's a non-trivial kind of cost there.
I see.
Yeah.
So it's sort of on a parallel path, and I guess people have talked about replacing like a Z Python with PyPy, but that's probably not going to happen in the near future.
Yeah, I've seen like some Stack Overflow questions and other things saying like, well, is PyPy just going to absorb Python and then become the new Python? So that's I think there's definitely people out there wondering the same thing, like, well, PyPy is getting these gains, what is there to lose? So it's definitely an open for debate topic. Thank you. Thanks for your question.
Thank you.
Cool. Do we have any more questions for Taylor, or should
I had a question specifically, like, so obviously lots of interpreters out there. What was the most, I mean, I think Stackless Python might check one of these boxes just by virtue of it being used primarily for EVE Online, but what was like the most specialized interpreter that you found? You're like, oh, why, like, where was someone trying to put Python that you would not expect to see Python?
That's a good question. I feel like I didn't go as broad as I could get a really good answer to that. So I'm probably going to just cop out and say this Stackless, like you were suggesting. But I think there's some Python for like embedded devices I think is interesting, because you kind of associate that with C and lower level languages, like stripping it down and making it available there. PyPy does some really interesting things to get its advantages as well. Like they strip out garbage collection and probably replace it with something like malloc or like a customized thing to do like a better memory management for a low level language. So I think there's more to learn about each of those that might make them more interesting. That's one thing that I thought was great about this presentation, was that the more I dug into one version of Python, the more I learned about the eccentricities of. At one point I was doing Jython and IronPython, and then I was kind of disappointed because I was a Java developer and I've always wanted to be able to write Java program that had embedded Python in it, and like Jules I think does that as well, but I saw that it was like 2.7 was the version of Python that it was compatible with. And so I was like, oh, that's pretty old, and I'm missing all these features from Python 3 that I'm now using at work, and I don't think I would enjoy coding in it. Although there's a lot of like core structure that's still the same. And so, but then I saw that like all the things that people were doing with it, and so I think it's more about like for the use case actually being able to communicate with languages that are more traditionally thought of as lower level than Python is more interesting than I thought. And I think Nagare, so I'm thinking more applications probably, and things I'd like to check out more after reading about them. I think Nagare was something that I like. Now I want to write something in it just to see what's different about it from React and Angular and all of the web frameworks.
I don't want to, well, thanks for the answer, but I also don't want to divert from like people asking about the presentation, but I have opinions in that space, so would love to chat after the meetup space.
Yeah, that'd be great. Thanks.
Well, we can do that very shortly. If there's no more questions, I can stop the recording. I'll go ahead and do that.